Hello, my name is Casey Kelly. Here's my student ID, and today we're going to be going through the paradox of the derivative. So we'll be diving into one of the most fundamental concepts in calculus, the derivative. This idea was developed by the two mathematicians, Isaac Newton and Gottfried Wilhelm Leibniz, in the 17th century. They created calculus to help explain the changing world around them. For instance, Newton used it to describe the motion of objects, and Leibniz used it to understand continuous changes in nature. But calculus isn't just about numbers and equations, it's about understanding change, specifically how things changed instantly. This brings us to an interesting paradox. How can we measure change at a single instant? So imagine you're watching a car speed down the road. We can measure how fast the car is going over a period of time. You can calculate its average speed by looking at the distance covered and dividing it by the time taken. But how do you measure its speed at an exact instant? Say at the moment when the car crosses a certain point on the road. It seems like we need a way to measure the speed without time passing at all. The paradox is that change requires time, yet we want to understand it at an instantaneous moment. This is where the concept of a derivative comes in. So the secant line, which stands for the average rate of change. So to begin understanding this, let's look at the concept of the average rate of change. So picture a graph of a function, like what you can see on the screen there. If we take 2 points on the graph, call them point A and point B, and draw a line through them, this gives us the average rate of change over that interval between A and B. So for example, if the function represented distance travelled over time, the slope of the line connecting these 2 points represents how fast the car is moving on average between the 2 points. Mathematically, the average rate of change between 2 points, f of x, and f of x plus h minus f of x, is given by the formula that you can see on the screen there, which is the average rate of change. H stands for the time between the 2 points. So for the tangent line, now if we want to know the instantaneous rate of change at one specific point on the graph, this brings us to what's known as the tangent line. As we shrink the distance between the 2 points, so point A and point B that we talked about before, the secant line becomes the tangent line, a line that touches the graph at exactly 1 point. This tangent line gives us the instantaneous rate of change. To make this more precise, as we take the limit of the average rate of change as h approaches 0, the secant line becomes the tangent line, and the slope of the tangent is the derivative at that point. So we'll talk a little bit about the exact definition of the derivative. So the formal definition of the derivative is the image, the formula that you can see in the image there. So that's the formal definition. So this formula tells us how to calculate the instantaneous rate of change at any given point on a function. Essentially, it answers the question, how does the function behave at an exact point without any time passing? The formula works by the following steps. So number one, f of x. This is the original value of the function at point x. It tells you where you're starting on the curve. So number two, f x plus h. So this is the value of the function at a point a small step away from x, where you've moved forward by a small amount, known as h. Think of h as a small step to the right on the x-axis. Number three, so the numerator on the formula, f x plus h minus f of x. This is the change in the y values, the function's output between the 2 points. The value after stepping by h minus the value where you started. In other words, this gives us the vertical change. So number four, what is h exactly? So this is the change in x, so the horizontal step you made. It is just how far you've moved along the x-axis. So number five, taking the formula as a whole, starting from f x plus h. So this is the average rate of change, or the slope of the secant line between x and x plus h. So the slight change in x. it tells you how much y changes per unit of x over a small interval. So now we're looking at where it says lim h tending towards 0. So this means we are making h smaller and smaller, getting closer and closer to 0, so that our 2 points are almost on top of each other. As h shrinks to 0, the secant line approaches the tangent line at the point x. So next slide. So we're looking at an example. So the example here is finding the derivative of st, where that is 3t squared. Okay, so the first one is we're finding the derivative, sorry, of s of t when it's t cubed. So the first derivative of that, what you do, a nice simple step rather than working through the whole formula, is reduce the power by 1 and move whatever value the power was originally in front of t. So you reduce the power by 1, so that become t squared, and then you'd move the 3 in front. So you can see the first derivative is 3t squared. And so if we input 2 into this, then we are left with 3 multiplied by 2 squared, which comes out as 12, which is the instantaneous speed, instantaneous units per time. So the object is moving at speed of 12 units per time. This is the instantaneous speed, as opposed to the average speed over an interval, because we're not looking at an interval anymore. We are just looking at the instantaneous speed. So this is just like a visual representation of what we just talked about. So as you can see, we have a square with area x. So around its perimeter, the length equals x and the width equals x. So that's x squared. So if we're looking at taking the derivative of x squared, then we can think of that as a small step along the x-axis of the graph from the point x squared. So as we can see, the yellow bars represent that slight increase. Okay, and also in the visual example, we can see where it says d of x. So obviously in the formula, d of x is actually represented as h. All this means is the slight increase. So as we can see, the increase in x squared is 2 x values and then 2 d of x values. But if we think about it, when we're finding the derivative, we look at the limit as h approaches 0. So in this case, as d of x approaches 0. So if that approached 0, then the area of d of x squared would be finite, would tend towards 0. So we are left with an increase of 2 x values. So the increase would be 2x. And if we were to put x squared into the formula, then we would find that the derivative of x squared is 2x. So that is just a nice sort of visual representation of how you calculate the derivative of x squared. Okay, so in terms of applications of derivatives, so why is all of it important? The concept of the derivative is used in countless fields, from physics to economics to machine learning. So in physics, the derivative are used to calculate velocity, acceleration, and other rates of change in the physical world. In economics, the derivative helps us understand concepts like marginal cost, where we look at the rate of change in cost or profit relative to the quantity of goods produced. And then in machine learning, derivatives are crucial for algorithms like gradient descent, and an example is shown here on the screen, which helps models learn by minimizing errors and adjusting parameters step by step. So in conclusion, the paradox of the derivative, how we can measure change at an instant, has been a central question in mathematics for centuries. Thanks to the work of Newton and other mathematicians, we now have a powerful tool to understand instantaneous rates of change, whether in physics, economics, or data science. Derivatives help us better understand the world around us, and they form a basis of much of modern science and technology. Thank you very much for listening.